Good morning, everyone, online and in person here. I hope you can hear me well. Today we have the honor of having very distinguished presenters about a topic that is really hot topic, but hydrogen production, the role of the storage and transportation related infrastructure. We are going to have three panelists, Thomas Jenkins, Yumin Lee, and Fabio Granchamp. Thomas is senior adjunct lecturer at Johns Hopkins University and seasoned consultant with the bank, and Yumin Lee, transport analyst with the World Bank. Good morning, Yumin. You're here as well.
Yep.
Great.
Hi, everyone.
Great.
Thanks for having me.
And we are having as well as a panelist Fabio Granchamp. He's connected virtually as well. I think I saw him. So
good morning.
Good morning, Fabio. Executive Vice President, CEO, President, Complex Brazil. So we have 1 hour and a half total time. We're going to start with Dolf Gilling. Dolf Gilling is going to be opening the session with some initial remarks. He's our lead green hydrogen and leading the program and H4D partnership, where I'm myself part of the supporting the program, work stream one on infrastructure, and we got other colleagues in the room also part of the team as you know. So I will give the floor to Dolf for a few introductory words, and we will take it from there with other presenters. Thank you very much.
Yes, thank you very much, Rafa, and hello, everyone. Thank you for joining for this webinar. I will keep my opening remarks short. First, I wanted to mention that we have a flagship report, Scaling Hydrogen Financing for Development. That was, let's say, the information was launched before COP already, before in end of November, but the full report is finally this week online on the ESMAP website. So please have a look there, because that's also a report that goes in detail into the issue of infrastructure. Second point is that infrastructure is really key in the overall development of the hydrogen economy. There's an increasing recognition that this is a very important aspect. And that if we talk about infrastructure, it has many aspects. It has the aspect of where does the renewable power come from? How do you plan the transmission lines? Where does the water come from? Often desalination is needed for electrolysis. There's issues around the hydrogen pipeline. How do you locate, for example, the electrolyzer? Do you put it in the renewables field, or do you put it next to the ammonia plant in the port, etc.? All these aspects are a part of what we consider infrastructure. And the World Bank activity in this field is increasing rapidly. Also, in this webinar, we will hear from Fabio about the activities in Ceará, in the port of Pecém. So that is one important activity. Also, the bank is engaged, but we are engaged elsewhere in Brazil also in infrastructure development, and we expect to ramp that up. In the last Hydrogen for Development Partnership meeting in Santiago in Chile in end of October, we had a special session on infrastructure, and there's also a background paper on infrastructure aspects for Chile. But also in Namibia, in Mauritania, in South Africa, the bank is engaged in discussions around infrastructure and port development for hydrogen. So expectation is that this going forward in the coming years will be a key activity for the bank and for our client countries. And I'll stop there and hand it back to Rafa, please.
Thank you very much, Paul, for your opening remarks. Yeah, this is a very, very relevant topic that we are really promoting at the bank, and we really want to help in its development in emerging markets. So over to Thomas. You have been allocated. We have a total 1 hour and a half, so we want to be going to have a good discussion at the end of the 3 presentations. So please, all your questions, unless they are bonding questions, very specific to the presentation, but please hold questions until the very end. And Thomas, you can floor is yours.
Yes,
for about 30 minutes.
Okay. It just popped on without that. Yes. Let me just pull this file. Yeah. Right. Sorry about that. Microsoft Teams is not my specialty, but we're set now. So I'm going to be talking about the role of storage and transportation and infrastructure more generally. Let me just start through this. So there's a significant difference between the levelized cost of hydrogen production and the delivered cost of hydrogen. And that's where we have to think about what you need to get delivered hydrogen. And that involves typically storage and then potentially moving the hydrogen a distance. It could be short distances, and that has historically happened in places like Texas, where there is a network of hydrogen pipelines that connect hydrogen production, grey hydrogen production, to ammonia plants and something similar. But more broadly, people are thinking about there are large differences in the cost of green hydrogen production, or blue, and that you might be able to connect the production to regions where it would otherwise be much more expensive. So there's a lot of interest in transporting it longer distances. And so in that context, we're going to be talking about here about giving a bit more background to these building blocks, which I would say bridge production essentially to delivery, and one's considering in the context of the lowest levelized cost. It's a very large area, infrastructure, and therefore, in 30 minutes, we're not going to cover everything, but the focus here is going to be on storage, hydrogen pipelines, and then considering them within the context of alternatives such as ports, shipping and ports. Okay. So some of these slides, I'll jump through quite quickly. This is a arena figure that sort of just generally sets the scene: production, transportation, transformation, and end use. This transformation idea is that when you move hydrogen from A to B, you might actually sometimes not move hydrogen. It might be cheaper or more appropriate to use a different type of energy carrier, and liquid hydrogen is particularly thought in that context with regard to shipping. But infrastructure costs, in terms of what this adder are, vary very widely, and it's going to depend on the sort of factors one would imagine they might depend on. The distance moved, the scale is in fact very important. Another thing is that when you connect the different building blocks, you have to make choices about the size of storage, the size of the hydrogen pipeline. For example, because you might have hydrogen storage that comes from production, that enables you to level out, in a sense, your hydrogen that would go into a pipeline, allows for a higher utilization and therefore a smaller pipeline. So these things are all interconnected, and utilization is a very important part of this. I'd say one more other thing from the research that I've done is there's a lot of interest in using existing assets where that's possible. Certainly studies that are looking at Europe in terms of the European hydrogen pipeline anticipate using a significant amount of repurposed natural gas pipelines. So we're going to step through the idea of storage first, then transportation, and then think about shipping and ports. So if we think about hydrogen storage, why have it? And so because the output of green hydrogen is variable on an hourly basis and on a daily basis, and in fact on a seasonal basis, because you'd be using wind or solar, you can use storage essentially to store that output or some of that output, and then enable it to balance the demand. So that's one thing you might do, but also storage might be used over longer timescales. And in that context, underground storage is particularly interesting because it's a lot cheaper, we'll see, than above ground storage, and also a lot cheaper than battery energy storage. An area we won't talk much about in this talk is that it's also considered a potential use in transportation, in which case you'd actually store it to something like 350 or 700 bar. You'll see that the storage that happens above ground is typically limited to about 100 bar, and it can be a little higher than that if you're doing it underground. So a picture is worth 1,000 words. So both of these examples are using above ground storage, and you can see the above ground storage in the figures. On the left hand side, which is a 260 megawatt electrolysis plant in China, you can see the 10 spherical hydrogen tanks on the left hand side where the arrow is. And on the right hand side, for a smaller 20 megawatt electrolysis plant in Spain, where the hydrogen is going to be used as a feedstock for ammonia to an existing plant, you can see those 11 cylinders on the right. And typically for above ground storage using tanks or cylinders, it's of the order of 20 to 60 bar. You get much higher pressures like 350 and 700 bar for transportation because you're dealing with typically much smaller cylinders. And in fact, there's another way of doing it, which is you can use pipelines. You can use natural gas, essentially pipelines, but you close off the ends, and that's also another way. And in terms of the sizing of this storage, I talk about sizing in terms of average daily production. So the example on the left-hand side has enough storage for, on average, 1/3 of a day's storage. And on the right-hand side, the plant has enough for 1 to 2 days storage. So as well as sort of balancing supply and demand on an hourly basis, you also might well have it for reliability. Certainly that's what's being done on the right-hand side, where they're thinking about having some backup storage to enable the ammonia plant to continue to run at a high capacity. So we've done some levelized cost calculations of what the actual adder is. And you can see on this figure on the right-hand side that I've got an example where you've got 1/3 of a day's storage, 1 day's storage, and in fact 2 days storage. And I've broken out what the levelized cost of that storage is in terms of capital recovery for the storage, for compression, and electricity. And so what you'll see is the top 2 bars, the compression and the electricity, are the same in each case, but you're having to pay more if in fact you have more storage. And I think really the takeaway from this is 0.3 to 0.7 cents per kilogram isn't a trivial number when one thinks about a lot of people discussing we can get this low cost hydrogen production. And my sense sometimes is with infrastructure, as you build it up, there's a possibility you might miss a component, and that could be valuable. Because if you don't have this storage, or rather, this storage is what allows the downstream infrastructure assets to have the high utilization that's often assumed to give them the low levelized costs. And on the right-hand side, you see liquid hydrogen, which is significantly more expensive. It's shown there at about $2 per kilogram, and certainly people are hoping to get it down to $1 per kilogram or less, but it is expensive. Some interesting charts that sort of summarize what underground storage looks like. I'm just going to show you the rock cavern on the left-hand side, and it's got a range of perhaps 50 to 200 bar that it can operate at. How high pressure you can operate at is quite interesting, actually. It depends on how deep in the ground you are. You basically need to be deep enough that the weight of the ground above you is sufficient to give you the pressure that you don't, I suppose, damage your salt cabin. The other thing is you can't go too low, because if you go too low, you'll start, I suppose, collapsing the cabin's inner walls. So they have a working volume of perhaps only 70% of the gas that's in there can be used. And I'd say one other thing is when you see that volume, you can, as a rule of thumb, consider it about 3 times more expensive than natural gas, because for the same pressure, natural gas has 3 times the energy density on a per unit volume basis. So this is looking at underground storage. And what it's saying is that the cost of underground storage can potentially be 10 times less than the cost of above ground storage. And that's $500 per kilogram versus $50 per kilogram. Now, I've actually translated that into kilowatt hours, because it's quite interesting if you look at that. $15 per kilowatt hour versus even down to $2 per kilowatt hour. And so you can see that within the context that a battery storage, I mean, arguably, when you move to certain types of batteries, it could get a lot cheaper. But if you're talking about something like $100 plus per kilowatt hour, these are very big differences for large scale seasonal storage. What makes the cost of storage a little higher when you're using a cabin is that you're not typically using it for daily storage, filling it every day. You're using it on seasonal storage, and you might have 20 days storage or so. So those things factor into what the levelized cost is. But it's still going to be, well, let's just leave that there. I might come back to that a little bit if I have more time, which I know I won't. So, so I'm just going to show you liquefaction of hydrogen storage. Again, we're trying to get through a number of ideas here, just to give you a sense of what's involved in storage. So it's very expensive. On the left-hand side, you see the bar corresponding to 1 is actually over $2.50. And then it's showing how it could go down under various studies. So why you would use it? It's about 10 times denser than on a per unit volume basis than if you compress gas to 100 bar. So that's a good idea, but it's very expensive. And the reason it's expensive mainly is that the liquefaction process takes up about 1/3 of the lower heating value of hydrogen, which is a lot. And also the capex associated with liquefaction is very high. So that's storage. We're on to hydrogen pipelines, and I'll acknowledge that Dov warned me about putting too much data on. So perhaps if this is circulated at some point, people will see this in more detail. But on the right hand, you see, the main point is you see a natural gas system that's in fact a hydrogen system. They're very, very similar. You've got hydrogen production from different sources. You can see the storage we just discussed, and you compress the storage, in this case, 100 to 200 bar. Or you could avoid the storage and go directly into the transmission pipeline. There's a distribution pipeline. So there are big similarities between hydrogen pipelines and natural gas pipelines, to the point that Europe is strongly considering large amounts of using existing pipelines. And the reason is that you can use steel pipes, you can use underground caverns, and these flow rate formulas look very similar, whether or not you're dealing with natural gas or hydrogen. The big difference is what I went back to earlier, that for a given pressure, the energy density is only about 1/3 what it is for natural gas, which really would mean that if I didn't do anything different, I'd have to have three times many pipelines, or I'd be delivering 3 times less gas. So what actually happens is you beef up your compressors to about 3 times the power, so that you actually can push through the volume at 3 times the rate. It's slightly limited. You can see it says 88%, because there are limits to how fast you want to push the gas through the pipeline, because it can cause some damage to the surface. There's some other issues associated with embrittlement and leakage that people have to think about, but overall, significant similarities. So we're talking about hydrogen pipelines and the cost of hydrogen pipelines. So there's a number of studies that look into this, and it is not uncommon to come up with an estimate like 0.2 to 0.3 dollars per kilogram per 1,000 kilometers traveled. Now, implicit in those estimates are that they are using large pipelines, typically 48 inches. They're talking about 1 or 2 million metric tons of hydrogen a year. And that's what's sort of indicated on the chart that we've got here. You've got a Canadian study and a Gulf European study, which have 1.5 and 2.5 million tons per year. And they're represented by those stars that fall somewhere between 0.2 and 0.4 dollars per kilogram per 1,000 kilometers. But if you look at a number of studies that do these calculations and you go to smaller diameters, 36 inches, 20 inches, which correspond to lower annual delivery of hydrogen, the cost can go up significantly. And this Canadian study is an excellent study that looks at this in great detail across a range of scales. But I think my point here is people may be talking about building 48-inch pipelines from Saudi Arabia to northern Germany, but you wouldn't be talking about doing it with a 20-inch pipeline, or you'd be talking about very different costs. And I've done some sensitivity analysis here. On the left-hand side, you see the cost per 1,000 kilometers for a 48-inch pipeline, a 36-inch pipeline, and this is from the European hydrogen study. I should point out quickly that these curves that you see are also from the, with the dots, are also from the European hydrogen study. Those are their estimates for a new pipeline. But if I change things, I mean, we use back of the envelope calculations in a way with a spreadsheet, but we can get quite close to the internal. Our internal estimates are similar to EHB, and then I revise it for a revised capex, discount rates, and capacity factor. And the takeaway here is these numbers can move quite a lot. And yeah, you certainly can see there's one that's over 0.7 dollars per 1,000 kilometers, and that's very different from 0.2. So these are the sorts of things one would factor in. That's the pipelines. And then the idea would be, if you were thinking about pipelines from going to A to B, certainly people are considering an alternative in terms of shipping. And ammonia is the one that people think a lot about. And here on the right-hand side is a figure from Hydrogen Insights from 2021 that's showing an example where you go from Saudi Arabia to Rotterdam, and you've got ammonia, liquid hydrogen, and alternative carrier. I mean, I think the real takeaway as I look at this is the error bars. I mean, they're large. You look at the top one on the left-hand side for ammonia, dehydrogenation. What that actually means is that after you've shipped it, that you, as ammonia, that you may want to reduce, take it back to hydrogen. And I'm saying that the number they're saying is $1 to $2 per kilogram to do that. And that seems enormous in size and also in variation. So that's quite interesting, because perhaps you don't want to change it back to hydrogen and you can use it as ammonia. So I picked this number of 8,700 so that we could compare it to this study and a number of other studies. The way you can figure out what these costs are is you have to worry about what's going on at the port itself. And so I've got some ammonia plants, I've got a pipeline, I've got refrigerated liquid storage, which is interesting in the sense that the number of days of storage would often be something like 15 days production. And it's 15 days production, could be more, for two reasons. One of which is to allow the ammonia plant to keep producing. And the other side of it is, on the other side of it is, perhaps more importantly, is that when you've got the ship, you want to fill it up. So in this particular case, you're seeing 4 ships arriving every week, well, one ship each week could basically take this 2.6 million metric tons of ammonia per year. And by contrast, neon, which is people talk about quite a bit, is about a little under half of that. So you could do something similar with ships that were half the size of this on this sort of scale. But it's quite interesting to look at that 15 days hydrogen storage, because this will show you why people come up with different values. So what I'm doing here is I'm looking at what the value of port to shipping to port is. And we've done some internal analysis, and you've got, it's a little different if you've got an existing berth versus a new berth. And then you've got some other studies. And so what the takeaway is that the bit in the middle, the green bit, looks like it's between 0.10 and $0.3 per kilogram. That's the use of the the export port. That's the blue thing at the bottom. And then you've got the shipping, and then I've got an import port, which I'm assuming is a bit similar, but in fact it might be cheaper because in fact it exists and you might use existing berths. But really what I'm trying to get at here is that there's a number of studies in the literature. They have somewhat similar values, but also somewhat different values. And one example here, you can see this DNV export port estimate of a recent study came up with $0.28 per kilogram for hydrogen. That's for a brand new port. And but there's huge variation because in that same study, they mentioned that you can see the blue right next to it for an alternative estimate is really, really quite small, tiny. And maybe that's because that's an existing port, but one of the reasons it was that in that alternative study, they only had about 3 days ammonia storage rather than 15 days. So there could be a wide variation in different studies. And so this is what's happening when you go from port to shipping to port. If you then add on the conversion part of it, you can see the yellow is basically the conversion to hydrogen to ammonia. And then on the other side of it, you then add the cracking back, which you may or may not add. And so the net result is that you see that the shipping cost itself for pipelines, the green in the middle, is much, much, much less than the cost for shipping. Sorry, the shipping cost for ammonia in a ship is much, much less than hydrogen pipelines. But, and this is the big but, there are potentially very large costs associated with converting the hydrogen to ammonia and back again. And that's why we've got to worry about both of those. How am I doing for time, Dom? Have I got 5 minutes?
Doing quite well.
Am I doing quite well?
I would say even 10 more minutes.
Okay,
Yeah.
good. That's sweating off my hand. So I don't went too fast, but I mean, yeah, so I think this is an important slide here. I mean, what you're seeing here is on the left-hand side, you've got sort of back of the envelope calculations with spreadsheets. And I'm just saying they're not so different from other people's studies. I mean, certainly if you wanted to do this properly, as you would, there's systems analysis, very detailed models, etc. But I think you can get a grasp for what's important in a relatively straightforward back of the envelope way. And when I say back of the envelope, I always say, the level of something like Lazard's financial analysis. And I think it is interesting to see, if you look at this the blue, green, blue, that there really is quite a variation amongst different studies. So there's a variation in the overall cost and in the breakdown of the cost. But shipping itself, the bit in the middle, isn't that expensive. It's the conversion on either end that means that that's what you need to worry about when you're thinking about it as an alternative to pipelines. And more, just to drive home this point, this is someone else's study, open access, so I put it up here, this figure. But they did calculations of what the cost of ammonia shipping is. So they are actually just looking at that green part here. And what you see is they've got these blue lines, a central blue line, dotted blue line, that's their range. But they're making the point that they looked at other studies. And these other studies are estimating the same thing. What's the shipping cost over a particular distance? I just want to really emphasize the variation there. And I think what that takeaway means is that you need to be careful when you use estimates from different sources, multiple sources, when you combine them together, because you could end up with a least cost option that is not your least cost option because these differences can be important. And this also leads to the idea that being able to replicate analysis on a sensitivity level is useful. So that's the variation for the cost of shipping, but it's at least or larger for things that have more the costly, like conversion. Certainly things on conversion on either end is going to depend on the scale a lot. I'm going to just touch on this slide that we talked a lot about liquid ammonia, and the reason we talk about liquid ammonia rather than liquid hydrogen, which seems to be consensus, at least in the near term, or for at least a number of studies, is because for physical reasons, physics really, the cost of shipping liquid hydrogen will be 1.5 to 2 times higher than the liquid ammonia carrier. The reason for that is that the energy density of hydrogen, while it's much higher on a unit mass basis, it's much lower on a unit volume basis. And at the end of the day, you would need to have 3 hydrogen vessels for every 2 hydrogen vessels to move the same amount of energy. And it turns out that you also have to pay more for your liquid hydrogen vessel because you would have to have sort of refrigeration facilities that were associated with keeping something down at minus 20 degrees rather than ammonia. Now, it's more complicated than that because it depends on what the cost of the liquid hydrogen is versus the cost of the liquid ammonia at the port. And you have advantages, big advantages. You don't have to crack it back at the other end. But these are the sorts of things to consider. So now we go and we look at the levelized cost of shipping, which we did before, and we add on some estimates that exist. And there's a recent study by Afra Rini, perhaps I should pronounce that in terms of the capital letters, but they've looked at 5,900 kilometer hydrogen pipeline linking the Gulf Coast to Northern Europe, 2.55 million metric tons per year, investment cost of 28 billion euros. So that gives you a size that this is large investments. And their estimate is that it's $1.32 to go 5,900 kilometers. I think it's an interesting question, given that goes from the eastern side of Saudi Arabia, or Qatar actually, across to Neom and places like that, whether or not you can use a pro rata basis and it might be cheaper than $1.32 if you're going over shorter distances. But the takeaway here is that those sorts of numbers, this $1.32, is in fact lower than the shipping costs, or at least quite close to it. So the idea is perhaps if you had very large volumes, there does seem to be a case of these pipelines, but at lower volumes, you can understand why people are talking about shipping. Okay, so we're actually this is really the last slide I really wanted to show for certain. It's showing this relationship between pipeline sizes and shipping. So what you've got is the levelized cost of transportation, somewhere between 0 and $4.5 per kilogram of hydrogen, and the distance traveled. And so you'd imagine that there might be, and certainly many studies do this, a linear increase in these costs with distance. The question might be where the intercept is. So let's look at the pipelines first, which are the, there's a hydrogen pipeline that's 48 inches, and you go up a bit, 36 inches, you go up again, 20 inches. So what you see on the 48-inch pipeline, 2 million tons per year, is what a lot of people are talking about when they say it's 20 cents or 30 cents per kilogram per 1,000 kilometers. And that's the example that we've been showing up to this point. But you see, as you go to smaller pipelines and smaller volumes, you get a rapid increase in the cost that it would take to move hydrogen in a pipeline. Now, you contrast that to if you used ports and conversions. So at the bottom, for some reason, I've got the port shipping port cost, and I've got a range there from about 20 cents to 40 cents. That's probably a low range. It certainly would be a low range by including imports. But what you see is that then, as you go further distances, the slope itself is much, much more shallower. That goes to the fact that I was saying that it costs much less to ship. But now what you have to do is you add on the conversion costs to ammonia to put on the ship, and there might be a variation of what those estimates are. So that takes us up, even if we go to the intercept, which is 0 to $1, perhaps to $1.50, and then we do the cracking back, which you might do in some cases, and that takes you up to the red and the dotted red lines. And so I think you're just seeing that at different scales, different things win. So I suppose on this example is if the one that's in the circle in the middle is showing you The green circle is showing you if you went this 8,700 miles, what would be the cost if you used it as ammonia. The blue above that would be if you cracked it back to hydrogen. And in that case, you see that the white circle is winning. The white circle is winning because that's the pipeline, because it's lower. And there's one other thing I should say that's quite important here, is that the white circle is at 5,000 kilometers and the shipping was at 8,700 kilometers. And that's because you don't compare like distances. When you the Saudi Arabian pipeline goes 5,000 kilometers to Germany, whereas the ship has to go around to Rotterdam. So that is the connection here. I know this is a bit of a heavy slide to look at, but it's perhaps worth looking at later. So what we see is that in this particular case, under this illustrative example, the pipeline was cheaper. But if in fact you had a much smaller pipeline, then it's not even close. And then it's much cheaper to do the shipping. So I suppose, yes, so that's what I'd say. So I think I'm finishing there. If these ever get circulated, you see a few more slides.
Perfect. Yeah.
These are Dolph's points here. So you need infrastructure to supply the end users and applications, and you want to do so at the lowest cost. The costs are big. I mean, they're certainly trillions by some estimates, but they're incredibly uncertain because it depends on what is the demand 200 million or 600 million metric tons in the year 2050. They're huge things. And then it depends on all of these things. And this is with me just really focusing on a number of areas. I really haven't talked about distribution, transportation, but my instinct is people can underestimate the infrastructure you need and just assume it's there and give themselves very low utilizations for their other assets. Scale matters enormously, and I really will stop there.
Very good, Thomas. Thank you so much. I think this is last slide on summary observations. We may come back to it at the end when the audience has questions. Actually, we have 72 people connected virtually right now, so that's excellent, and some colleagues in the room as well. We should go to Yao Ming. You have a question?
Can I start? Yeah, actually.
But we will.
Yeah, but maybe we should, ask for prioritize the guest rather than me.
No.
Oh, well, we will do questions at the end.
Okay.
Because we got two more presentations.
Okay, I see. Okay.
So I think this is good to recover. Otherwise, I think it's we agreed on unless there is a burning question. I mean, we will do those at the end. And I would like to now give the floor to Yuming Lee.
Did I stop sharing, mate?
Yes, great, thank you. So Yuming is a transport analyst with the bank, and we will hear transport perspective on that end. Yuming, I think we agreed on about 12, 15 minutes maybe a presentation. Is that fine? Yep. So I would like to have like a good 15 minutes at the end, at least to have a good discussion after the third presentation. So over to you. We see your presentation. Thank you so much.
Okay. Thank you. Yep. Hello, everyone. My name is Yuming Lee, transport analyst at the World Bank Global Transport Global Unit. Thank you very much for having me as a panelist today. And while Thomas gave you a very technical part of how hydrogen infrastructure and its transport, I would like to give you an overview of what Maritime of the Transport Global Unit is doing, combined with the hydrogen agenda and hydrogen and decarbonization agenda. So the maritime industry accounts for like 3% of global emission, making shipping the 6th largest emitter worldwide, which is more than Germany's entire annual emissions. And there has been a lot of significant global attempts of decarbonizing maritime transport, especially with the IMO, which is International Maritime Organization, declaring decarbonization as a top priority. So for example, in 2018, the IMO has already declared to reduce 50% of GHG emission reduction by 2050 with incremental reduction targets in 2030 and 40. However, they've decided to take even dire attempt by revising the IMO GHG strategy for adoption, net zero GHG emission by 2050. And on top of that, the revision of the EU ETS kicked in to include shipping from this year, January, which just happened. So shipping's energy transition is a big challenge. It always has been. And largely this can be done through increasing the energy efficiency. And this attempt has been quite successful in the past years. However, in order to meet the ambitious target, we can't ignore a zero carbon fuel agenda. Okay. Yeah. So, as Thomas mentioned previously, in our internal estimate with the estimated scenario, we see that decarbonizing shipping sector brings in multi-trillion-dollar investment opportunities. And as you can see from this graph, this is more significant in land-based investments such as hydrogen production, bunker infrastructure, alongside the ship-based investment itself, such as developing engines, onboard storage, etc. And of course, there has been a long discussion on the chicken and egg problem and the alternative fuel uptake. However, I personally believe that this conversation is now outdated. And now we clearly see that there is a strong demand coming and the number of ships in operation for carrying them, as you can see from these graphs. With the recent conversation we had with Maersk, one of the biggest shipping company, they're also planning to order more alternative fuel powered ships as soon as the engines become available. And we see that that's coming very soon. So to navigate this grand transition with our clients in the global scene, we followed a two-pronged approach to make sure that Global South is also engaged in critical conversation and benefit from this transition, not leaving anyone behind. So in these aspects, we have two approaches. First one is global analytics and policy work, and the second one is engagement inside in our client countries. So our global analytics, for example, we carry out an assessment among all countries and identified prime producers for future zero carbon shipping fuels. So those fuels can be green hydrogen, but also green methanol and ammonia. And many of the countries that we work in have a significant renewable endowment, which makes them very suitable to produce ship fuels for the future. So this can unlock new development opportunities and realize co-benefits such as clean energy and job creation. So especially what we've done is that we analyze the three main categories of zero carbon bunker fuels to see which has the best potential to replace heavy fuel oils for ships. So one is biofuels, where biomass from plants and agriculture waste is transformed into fuels such as biomethane, bioethanol, or biomethanol. And also the second one, what we're currently discussing is there are also hydrogen and ammonia, where green hydrogen is made from water, using renewable electricity, and also blue hydrogen that we also looked into is also made from natural gas, where we capture the carbon and store it securely to keep it out of the atmosphere. And lastly, we looked into the synthetic carbon-based fuels, where we combine green or blue hydrogen with carbon takeout to the atmosphere to produce synthetic methane or methanol. And we assessed these different fuel categories against that of environmental, economic, technical, and safety criteria. And we found out that green ammonia and green hydrogen are currently the most promising options to decarbonizing shipping. Mostly because it can be produced at a very large scale. Just Thomas mentioned, the scale is very important and likely to be most cost effective in the long run and offer enhanced flexibility. And based on this, we quantitatively assessed 218 countries around the globe to get some idea which of them may be well positioned to produce zero carbon ammonia and hydrogen for the shipping industry. And we use 5 key criteria, which is energy resources, shipping volumes, geographic location, regulatory framework, and the potential to use of these existing infrastructure. And based on the global scoping exercise mentioned earlier, we worked with selected client countries to develop a groundwork for investment project as well, moving forward. So for the pilot projects, the Transport GP Maritime selected South Africa, Morocco, and Colombia, which are all considered as high potential countries. And we're currently conducting a pre-feasibility studies in selected ports in these countries to produce and export green carbon fuels in the future. So just like the maritime industry, maritime is a gateway for trade. We're also seeking a gateway for synergies with other sectors through the maritime decarbonization. So most prominently, of course, the energy sector producing green hydrogen and ammonia requires firstly significant amount of renewable electricity. So in many of our client countries, affordable and clean energy is constrained. However, investing in green fuel production will add a net benefit of extra green electricity to the grid. And secondly, producing green hydrogen from renewables can be used beyond fuel production. For example, local heavy industries such as steel making can bring in jobs to these developing world. And especially in South Africa, we are actively discussing about this synergy as well. Thirdly, green ammonia will be an export commodity. Just to name one example, for example, the European Union and other countries such as Japan, South Korea, to source green ammonia from Southern Africa. Finally, the latest policy signal from the IMO that shipping will follow a more ambitious decarbonization pathway gives confidence that ships will be using zero or near zero carbon fuels very soon. So one core element of revised IMO strategy is that the 5% clean fuel target, meaning that 5% of shipping energy mix shall consist of zero or near zero bunker fuels by 2030. Of course, the private sector will have to play a significant role, and the aim of the World Bank is to attract more private capital to projects in lower income countries. Still, especially it's in the very early years of transition, and private investment must be de-risked to happen. So here, the World Bank offers broad suite of products tailored to governments, state-owned enterprises, but also business through the example of guarantees, which is MIGA is doing as of now, and concessional finance, but also quasi-commercial loans through the IFC. The hydrogen for development should also be thought one step further to make sure that we achieve an equitable transition, leaving no one behind. The World Bank has emerged as a pivotal advocate for these transition in global policymaking. And in line with that, we are actively contributing pertinent policies to the IMO negotiations. So this is particularly important for countries with low capacity, and they typically struggling to deal with this complexity of international policymaking and have relatively limited sources to participate in this process. Here we aim to provide an informed and unbiased view in this sense. And we are also part of FinSmart, an initiative jointly led by the World Bank, the IMO Secretariat, and European Bank for Reconstruction and Development, EBRD. So we aim to promote investment into green shipping and bring together major players from financial community to discuss how capital flow can be directed towards greener maritime transport. And this initiative will be even more important in the context of more stringent greenhouse gas reduction targets, which the IMO just adopted. And one more step further, I think I'm going one more step further. As part of engaging with the IMO policymaking process, we're also exploring the benefits of carbon pricing to reduce emissions from ships as well. As a financial institution, we're particularly interested in how income from such global market-based measure can support an equitable transition for developing countries. For the most recent report we've published in June last year, deals with the question on how revenues could be distributed in the most efficient way. So I think this is the short overview of the World Bank's Maritime Decarbonization Program and its related projects. And happy to answer any kind of questions that you have, and I'll hand it over to the next panelist, Fabio. Probably he'll speak more about Port of Pessim project and how they're leveraging port infrastructure in more detail. Thank you.
Thank you very much, Yumin. Super interesting and focused presentation. Thank you very much for adjusting very well to the time allocated. So I would like to now give the floor to Fabio Gracham, Executive Vice President and CEO at FSM Brazil. Thank you so much.
Hello, everyone. Good morning to all. First of all, thank you very much for having me in this panel and providing us the opportunity to speak a little bit about PSM and the efforts we're making towards our infrastructure over here. So I'm Fabio Gracham. I'm COO of PSM, and my presentation here to you is basically twofold. I'll take the liberty of making a brief introduction of PSM for those who do not have that context, and afterwards I dive right into the infrastructure topic. So the port here, the PSM, is really a key enabler of development of our region over here, right? So basically, my colleagues and I, we have not only the responsibility, but we also have the challenge of creating social value, socioeconomic value and impact based on inclusion, basically, right? So we need to make sure that benefits of the values that we create here positively impact all of our stakeholders. So not only really our shareholders or customers, but our people, our employees, the communities around us, the state, and our local providers as well, right? So going a little bit more into the blueprint that we have today. I mean, although the port has been established since the early 2000s, this blueprint that we have here today, it's ongoing since 2018, when the Port of Rotterdam became a shareholder of the company, acquiring 30%, and today, is partners with the state of Ceará that holds the other 70% of the company. And the company today has basically two main business. The first one is the port in itself, and the other one is the industrial development in the industrial area over here, which in itself is also split in two. We have regular industrial areas, and we also have incentivized free trade zone areas as well, which are the ones in yellow. The business model that we have as a company is a platform for development as an infrastructure provider, and in that sense, energy transition, in particular, green hydrogen, is a huge opportunity for us over here. So as you can see in many studies, PSM has a very important and competitive position, and of course that brings us a huge potential in attracting billions of dollars in investment. So when it comes to this opportunity, and we combine with our business model, which is providing infrastructure, we basically have two interconnected challenges. So we need to, first of all, bear in mind that green hydrogen market is yet not mature. Many questions and uncertainty are still there. So the first challenge that we have, and that goes a little bit in line with the presentation of Thomas, is the fact that we have to provide infrastructure in a way that we're able to help in keeping the competitiveness that we have, and not really damage the competitive position that we have. So until the market maturation is there, and we cannot really tap into the full potential of economies of scale, what we're doing is we created this concept of green hydrogen hub, which basically is a concept that has its foundation on shared infrastructure. so in a way that we can combine and pool all the volumes of the different producers together, and make sure that we reduce costs as much as we can and keep up with the competitiveness until the volume is high enough in order to be able to have a little bit more dedicated infrastructure and so on. So in that sense, what we promote here, we basically have 3 pillars that address the 3 biggest cost elements of hydrogen production. So one is facilitating the power connection. As you might know, we here have a very interesting competitive position, which is we are able to connect the production of hydrogen directly into the grid, and that basically addresses some of the challenges of hydrogen production, because you basically are able to produce green hydrogen and green ammonia constantly over time without having much of fluctuations. So and facilitating this connection to the grid is one element that we believe it enables competitiveness. The second one is the supply of water. And although and Thomas addressed that in his presentation as well, that desalination is a way to go in green hydrogen production. For us over here, of course we're close to the ocean, so this is definitely an alternative. But we would even like to promote as a first solution for water supply, which is the reuse of sewage water coming from the big city Fortaleza that is close to us, and having that water treated, supplying into the production of green hydrogen. So that would be then the second shared infrastructure and utility. And the third one is really the network, the pipeline network connection between production and storage, and then afterwards the ship operations. So all being used in a shared way in order to optimize costs and competitiveness. So that's basically what we envision in order to create an environment, particularly to support the ramping up phase of these different plants. But of course, at the same time, we also need to make sure that the infrastructure is future proof, and that's basically our second challenge. And in this second challenge here, we have the support of the World Bank supporting us in expanding our port infrastructure over here with the expansion of 2 piers that we have, and they're both gonna support green products, be it directly with ammonia, for example, but also other green products that will benefit from the green hydrogen or green fuels that we're gonna have available in the complex. Part of this infrastructure, it's really connecting the production zone over here through an optimization corridor that connects this production here with the port directly. So this is basically how we are addressing infrastructure in these two points. One a little bit more focused on making sure that we provide the right environment for the projects to take off, and then the second really in a more sustainable way, providing in infrastructure for a longer term. So that's basically what I wanted to share with you. I hope that's clear, and I would love to receive some questions and have a discussion about it. Thank you.
Thank you very much, Fabio. Very interesting presentation again, and I think the 3 of them are very complementary, and I think we already are receiving several questions over the chat, and this is great. Maybe we should start summarize with the questions on the chat, and we can take it from there. And then please raise your hand online, and then we have other few colleagues in the room. Well, there's an overall question about the need of adaptation of boats and ships that we already have at the moment for transport and ammonia. That's one. There is another technical questions for Thomas about the figures you gave on if the cost per kilometer assume new pipelines or repurposed.
Shall we answer?
Let me
Okay,
just
yeah.
I think because the other questions are also maybe with you, and there is another one. About also transport of ammonia. I was not able to finalize reading, but I think that question from Rico, actually, he has been quite involved in some World Bank studies. Rico Solomon can do it verbally as well. So I would like to have maybe 2 more questions from the audience, so we can start this overall initial questions. We have still, 20 minutes to go. So let me see if there is anybody else in the audience that would like to add to these initial questions, or from the meeting in person. I think, Hiro, you had some.
Well, quick questions. So,
okay, so
Sorry, I would like to add. Sorry, were you doing questions? I missed that.
Yeah, if you have I was just reading a few questions on the chat, summarizing those and asking if there were people online. Let me see.
I have a question for after.
And let's see if there is a hand here. Okay, from Hiro and from Joseph Colonia. So will be your question.
It has to do more with sort of like the climate approach or the emissions approach, and going back to this idea of the route from Saudi Arabia to the Netherlands. Is this going to be green ammonia that is going to be transported? What about factoring in the emissions that are associated to the shipping, but also just sort of thinking about the overall argument for the shipping to the Netherlands, where I assume the energy mix is already pretty green. If it's a matter of, land availability, I understand the economic arguments for the shipping, but I'm wondering, what about if we start looking at, the climate argument as well, and if there's any estimates for this cost of emissions.
Right.
But we can come back to it.
Right.
Thank you.
And from Joseph Colonia and from Rico, your questions should be addressed to Thomas, so he can start with taking these initial questions, and then Bobby and Yumin can add to them.
Yeah, my question is indeed for Thomas as well, mostly on storage. You presented a few examples of half a day to 2 day storage. And I'm wondering if you see that as a must next to hydrogen production side, but also for end users such as steel plant, for instance, or large industrials who could need a stable supply of hydrogen. So if you see it as an emerging solution in most hydrogen projects.
So on the store.
Yeah. So I'll start with this. Thank you.
On the storage, when I was initially looking, I've sort of researched quite a lot of material. It was initially I was saying you've got this green hydrogen production. It's going to be variable on an hourly basis. If you're going to move it a significant distance, perhaps in a pipeline or anything, you want to be able to fill the container that you're moving it in efficiently, and therefore I think there's a strong argument for storage as a buffer that takes the green hydrogen that's close to the green hydrogen and then enables it to move to the next stage in an efficient manner. But you're right that when it gets to wherever it is, which might be, for example, a ammonia plant, then they certainly might want to have a few days storage of ammonia so that they know that their ammonia plant will win flat out. So I think I think it's a very good question you've asked, and the only thing is you could sort of collapse the distance, and if in fact you had the plant that was right next to the green hydrogen, then in fact that is the storage. You know, you've got the storage that's coming out of the green hydrogen. You store as much as you want so that you've got a secure supply to the plant that's next door. Now, when you say, well, I'm going to move it 3,000 miles in a pipeline, then in fact you want to have enough storage so that you perhaps fill that pipeline efficiently. But there is other storage that would be involved, because at the other end, you'd want storage that would be available for that. And it gets into bigger things as well, because as I was reading this about seasonal storage as well. I mean, if you're losing lots of green hydrogen, it's got a seasonal variation. And so if you've got a pipeline network, you may well be using salt caverns to store in there, so that you can, to the extent you've got a network, say in Europe, that had lots of storage caverns, then in fact they would be able to provide the reliable supply to the end user. So I maybe to step back from everything you just said, I think storage is important. I mean, it could be at both ends.
Maybe on the other questions, we can go over here.
But before that, maybe Fabio is going to answer something. No? ECT question?
Yeah, I mean, I would like to, of course, invite all this. I'm just trying to see if there are specific questions for Thomas, and also, I mean, I actually
on a very brief technical question I just saw was,
yeah,
did I use new pipelines or repurposed pipelines? Because it's a very good question. And so no, the estimates that you saw are for new pipelines, and so there is certainly a lot of interest in using repurposed pipelines. You will see estimates that the cost of a repurposed pipeline might be as low as 1/5 of the cost of a brand new pipeline, but it doesn't reduce the cost of the compressors. In fact, they will be larger. And I think one thing I've sort of read in the literature and people have talked about is it doesn't necessarily translate into such a large drop in the levelized cost of energy, because if you reuse an existing pipeline that has an existing asset life, I would imagine that existing owner wants a return on his asset base. So it's it certainly reduces the investment requirements. It's a more interesting question. It's a slightly different question, how much it reduces the levelized cost of hydrogen.
Great. Thank you so much, Thomas. So I think over to like now to give the floor to Fabio on adding on this, and also there was a question on potential modification needs for ports and so on. And after that, yeah, I'd like to invite Yumina and Rico also to add on this. Thank you. And
Okay.
now you are in line.
Thank you so much. Actually, thank you so much for you all to share the very the sophisticated viewpoint between the green hydrogen versus green ammonia. But on the other hand, I'm quite interested in the importance perspective in terms of competition between the green one and the blue one, and especially maybe one of the biggest, how can you say, impact that importers is very interested in is the turquoise hydrogen. This is a Mitsubishi's paper. And then according to them, since turquoise hydrogen does not emit CO2, so the importers like Japan or Korea, just import the LNG from the Houston or from Brazil by LNG ship, and then finally they can convert it to carbon and then hydrogen. Again, no emission of CO2. So that's why only how can you say, the catalyst equipment is needed, and then no other new equipment is needed. So that's why, as far as I understand, one of the biggest importers like Japan is very, how can you say, conscious about this impact of the future, compared to the cost of the hydrogen or ammonia. So may I ask? Actually, I'm quite unclear to whom of the three people, three experts I should ask. But if any three experts have any opinions, I'd like to hear your insight. Thank you.
Yeah, let me invite Fabio and Yumin to respond to some of the question posed. Thank you. Fabio, there wasn't a specific question actually on the, if you saw on the chart on ports and infrastructure, if there is any major needs, and let's see from Ricardo, and I think we would like to ask you and Thomas and Yumin about to understand the adaptation of ports and ships that we already have at the moment for the transport of ammonia. If there is any need, I guess mostly on the related to the hydrogen and on the ports. Thank you.
Sure. If I could just come back a little bit on the storage question that was posed to Thomas, and share a little bit of the experiences that we are having in our projects over here, because I think this is super relevant. Storage, as Thomas already anticipated, is mostly related to the capex that it's involved. So the bigger the storage, the more expensive it gets, as he showed with numbers as well. And for us, twofold on these one here. First of all, the connection directly to the grid and the possibility of operating 24/7 that reduces the amount of storage that you would need in the production of hydrogen, specifically, particularly if you're going to convert that into ammonia. So that storage is quite limited because of that possibility. And when it comes to the storage of the ammonia, what we are designing here is even this buffer that Thomas referred to. We in order to reduce that buffer as much as possible, what we're doing here is we are limiting the buffer of the individual producers, and then complementing that buffer on a kind of shared buffer among all the different producers. So the overall size of the investment in the storage becomes less. So this is one of the actions that we're taking over here in order to make the solution a little bit more competitive. When it comes to the question about the port infrastructure, our export product over here is initially being fully focused on green ammonia. Ammonia, of course, as you know, it's a regular chemical product. So what you have to really make sure is that you refurbish or refit your pier, your berths, in order to deal with that chemical product. But it's not much more than that. So we do have some infrastructure that's existing here at the port, and we're even expanding that a little bit further with two extra liquid berths. So what we basically need to do is retrofit the superstructure in order to have all the pipelines for green ammonia specifically.
I would like to add on the shipping perspective for that. So Fabio has given the idea of ports, but for example, in terms of ammonia-powered ship, like Mark said, that they're also planning to order ammonia-powered ship as soon as the engine becomes available, but they're kind of like seem quite reluctant in dealing with toxic of its, given the nature of ammonia, but they're like fully aware of the fact that how difficult it is to scale up the e-methanol without any biogenic source of carbon dioxide. So pretty much very similar what the port sector is currently seeing as of now. It might take some time to get there, but there definitely is an interest in that. And I also wanted to ask the Haruki, I actually couldn't understand what the exact question was. So I know that you've shared your screen and you try to ask a question. But
yes, my simple question is that we learned here the comparison between the green hydrogen versus green ammonia. But I'd like to know your insight about the comparison between the turquoise hydrogen. I mean, it's not a blue, accurately speaking, because as for the importers, turquoise hydrogen should be one of the most competitive, cost competitive options, including the capital cost. So that's why I'd like to know if you have any insight about it.
So basically, you know, of course, when we are talking about green hydrogen, and also, like I said briefly through my presentation, we've also looked into like blue hydrogen, which is made from natural gas. But we've actually did not like specifically look into like turquoise hydrogen or like anything more than granular than that. So from my end, I wouldn't have anything to add further than that. But I don't know if Fabio or Thomas, if you have anything to add on that.
Yeah.
I looked into turquoise hydrogen a little bit, and I think your statement's wonderful. I mean, it basically is a reaction where, in fact, the carbon's solid rather than carbon dioxide. So, in one sense, what's not to like? And I think what we found when we looked into it is it's still somewhat an early stage technology in terms of what would it cost to do at scale. And there's different ways that they're thinking of doing it. But my instinct is, if the technology is there that you can do it, that's fine. But then I also remember someone also said to me, so okay, so you store this solid carbon that you're happy enough about, you put it on a car, Dolph may have said essentially, and then in 10 years, when the tires finished, if it was burnt in a cement plant, Jim saying, then it goes back. So what would happen there? So I'd say that would be my thought. I mean, I think it sounds a great idea, and certainly one should look at it. And I think one thing I gave the wrong impression was that it was, ammonia, green ammonia was a winner, and we'd figured this out. I think what I was trying to emphasize a bit more was there's tremendous uncertainty in these conversion costs. Whether or not you convert the ammonia back to hydrogen could make or break whether hydrogen is better to ship, for example. The other thought I heard was that we hadn't done grid connected. I think grid connected makes, of course, a huge difference because your capacity factor goes up through the roof. But the question is, how much does your electricity cost? Because you've now got firm dispatchable electricity. So that's once you can connect to the grid, like they do for electrical cars, then yes, the production of everything's going to go up hugely. But the question is, is it $20 or $30 per megawatt hour, or is it you're paying a capacity factor in $70? I mean, I don't know the answer to that. And then the final point is we simply haven't looked in work we've done recently about the carbon life cycle effect, but of course that's something that would be looked into and should be looked into to fully understand it.
Thank you. Great, thank you so much. We have a few minutes left. I would like to maybe give the chance of 2 more questions on to the audience, and so Dolph afterwards can close the session. And actually, I'm happy to see there's a question in over the chat by Ana Maria Ruz. Good to see you, Ana Maria, in the audience. If you want to pose the questions verbally, otherwise I can read it. This is to Fabio. You know from Chile that but she's asking Fabio, Ana Maria, how long it took to 2% to arrive until this point, and if you are looking for uptakers mainly in Europe or as well in Asia, and for example, I mean, the Panama Channel is an issue for you.
All right. Thank you for the question, Ana Maria. So starting with the first one, how long it took us to get where we are? Yeah, I think it was a long journey, to be honest, right? I mean, and it took us a lot of interactions and learnings for us to get where we got. So initially it was all okay. It's a huge opportunity. Let's go after producers and all that. And then afterwards we realized that the initial part would be difficult. So how do we make sure that we bring a competitive solution to that, rather than having each of the producers, for example, having a desalination plan, each of the producers having a specific port connection, each of the producers having an ammonia tank and all that. And then we said, okay, that's a little bit not only cost inefficient, but it's also unbearable for the port. I mean, if you have 10 different hydrogen plants, you cannot really allocate 10 different berths for it. You cannot have 10 different tanks for it. Then we came to the realization that we needed one common operator for that, and that's what happened. And even after that realization, then we realized that it was not only the selection or the decision of having one, but we said, okay, if we're saying that there's going to be one operator, it means that we're creating a monopoly. So that also means that we need to get a little bit more involved into how that commercial and operation relationship is going to work. Otherwise, we create a problem to even a second problem to our situation. And then we realized that we need to get in the middle of that. So today we not only design the concept of the hub, but we participate and lead the creation of it. So that was also a role that we only realized that we really need to get into that, in that level and intensity of involvement around a year and a half ago. So that was a recent thing. And that's where we are right now. We are in the selection of this operator, for example. We are in the agreement with the water supply. That's exactly where we are today. So that was your first question. In terms of off-takers geography, I mean, conceptually, it seems that Europe is the most obvious off-taker market initially. So that's at least where we are mostly getting traction from the market in this part of the world over here. Although it seems, at least, I mean, Thomas was studying about that, but it seems that the cost of transportation in the end, it's relevant, but it's not really a deal breaker. So at least that's what we see in the Bloomberg study, that we can also be competitive in supplying green ammonia to Japan, to Asia. We have to see how that's going to pan out, but I don't think that's going to be our first market to be reached, to be honest. And lastly, Panama Canal is not really a restriction for these kind of ship. The ship in the end, it's not big enough to encounter a restriction of the Panama Canal. We're talking about 80,000, 90,000 square meter of capacity, which is from a Panama Canal perspective, not an issue.
Thank you so much. Thank you so much. Great presentations and very, very interesting discussion. We have almost reached the end of the discussion. Unless there isn't any other question from the audience, I'd like to give the floor to Dolph to close for the last couple of minutes. Thank you so much.
Yeah, thank you very much, Rafa, and many thanks to you, Fabio, and Thomas for their interesting insights. I hope through this discussion we've given you a flavor of the topic. You heard that infrastructure costs are significant in terms of delivered hydrogen cost, and also in terms of investment needs. So there is a role for financing institutions such as the World Bank to step into that. I think you also got a sense of that the optimization of all of this is not that simple. There are many dimensions you need to consider as you design the infrastructure. So there is an engineering aspect. There is also an economics aspect. We briefly touched only upon the issue of the common user infrastructure and how do you price infrastructure and how do you avoid that you create monopolies and all these aspects. So clearly more discussion is warranted, and I'm sure we will have further discussions in the coming months and years on this topic. So thank you very much for your participation, and we would also like to continue the discussion. So if you have further discussions, let us know, further questions and comments. And we will have regular webinars on various topics, and I think the next one is scheduled for next month to talk about Africa power sector integration for hydrogen. So thank you very much, and have a nice day.
Thank you very much, everyone. Appreciate it.
Thank you.
Thanks. Bye.